Okay, then thanks a lot to the organizers and also to CERM. I mean, I'm always amazed by how beautiful this place is. So I will be talking about how to use a distance between random parameters in Bayesian non-parametrics, which basically means that as parameters you will be considering infinite dimensional random quantities. So the setup, the problem that we will deal with can actually be phrased also in a parametric setting. So let's start from there. So if you consider the most simple Bayesian model, so you have observations that are conditionally IID given your random parameter, then you'll know that to perform Bayesian inference on the parameter, you first of all have to choose a prior, then observe the data, and finally update your prior with the data through conditional probability. Now, one of the most important features, but also one of the most controversial ones, is the fact that your inference on the parameter will depend on the choice of prior. And so a very natural question is the following. Considering now two different priors, and you observe the same data for these two priors. So will the two posteriors get closer to each other? And as you see more and more data, will they eventually merge? So this is a kind of a foundational question that was dealt with in this famous paper by Blackwell and Dubins in the 60s. And so the answer that yes, there will be merging of opinions if the two priors are absolutely continuous, one with respect to the other. So this is a kind of a sensible assumption when you live in a parametric world, basically thanks to the Lebesgue measure, I guess. But then what happens is that when you deal with infinite dimensional parameter spaces, even the most common priors often do not satisfy this assumption. And so basically what we do is to try to develop a framework to study and assess the merging of opinion in a non-parametric framework. The main idea is very simple. So it is that a natural way to quantify your merging of opinion will be to use a distance between posterior distributions. And now once you do this, you can actually answer many interesting questions. So first of all, of course, will there be merging of opinion? Which now we can translate into, does the distance goes to zero as the number of observations increase? But then we can also ask not only if there is merging, but also how fast the merging rate goes. So what is the merging rate? Because basically we not only have a notion of topology, but also have a distance that enables us to speak of rates as well. And then we can also ask other questions of the type, when does the merging start? So when I see the first observation, will the two posteriors immediately get closer to each other, or do I have to wait for a while before I actually can see the merging happen? So the nice thing about phrasing this problem in terms of a distance between posteriors, I think, is that basically we can avoid any of the usual assumption on the true data generating process of the observations. So for example, we do not have to assume that our real data is actually IID from some true distribution, nor that the observation actually come from one of the two models into consideration. And this is basically because instead of looking to how close the posterior goes to some true value of the parameter, we are actually looking at how close the two learning mechanisms are. And so basically it can happen that the two learning mechanisms converge, but maybe they do not converge to the truth as well. And so for our setting, basically, it will not matter if there is converging to the true value of the parameter, and for what it's worth, the true value of the parameter may even not exist. So if the parameter is finite dimensional, so in a standard Bayesian parametric setting, we could use many distances between the posteriors I don't know if you're familiar, for example, with the Wasserstein distance, but maybe you could use also Hellinger or maybe divergences. I mean, there are many common options. Now, the problem is that in our setting, our parameter space will be infinite dimensional. And so basically, also the definition of the distance that we're going to use is part of the research itself. Now, in a finite dimensional setting, in this interesting work by Ley, Reinert, and Swan, they actually used the idea of using an L1 distance between distributions on R, and we will try to generalize that. A snapshot, let's say, of the findings is that the merging of opinions in a non-parametric setting is actually a totally different problem than in a parametric one. So the merging can occur, but it can also not occur. And by this, I mean that even for most common priors, okay, not like specific counterexamples built ad hoc. Then the merging rate can actually change according to the prior that you're using. And finally, the merging can both start immediately in some cases, or even after a while. Okay, so this is the outline. First of all, I will give a brief introduction to Bayesian non-parametrics, so why we need it and what are the most important concepts. Then I will discuss why we need a distance between random measures in this context. And going on, we will actually define this distance between random measure using the theory of optimal transport. And finally, we will look at some findings in Bayesian non-parametrics. Okay, so the model we discussed at the beginning of the slide, you all know it's very nice because it's, I mean, among other things, but it brings to a coherent notion of inference. Moreover, it allows for a natural quantification of uncertainty, and what is often neglected, also to a natural way to encode predictions. But are these models flexible? So here the situation becomes a bit different. Basically because if you're using a finite dimensional parameter space, then you're actually embedding it in the space of probabilities for your distribution, which is an infinite dimensional space. And so this is the main idea of Bayesian non-parametric, to enlarge the space of your parameters and make it infinite dimensional. And usually the infinite dimensional space that we use as parameter space is the space of probability itself. So in a Bayesian non-parametric context, the random parameter theta is now a random probability p. I usually call it p tilde to underline the fact that it's random, to not create too much confusion. And so a Bayesian non-parametric model, the most simple one, looks like this. You have data that conditionally on a random probability come from the random probability, and then of course you need a prior for the parameter, which will now be a probability distribution on the space of probabilities. So it's quite easy to see that these models entail exchangeable observations, in the sense that their law is invariant by permutation of the indices. What is even nicer is that it is an if and only if. So this is a definity theorem, which tells us that for every infinitely extendable sequence of exchangeable observations, you have that there exists a random probability such that the data are conditionally IID. So basically what this means is that in practice, whenever you think that the order of the observation is not important for your analysis, you cannot be more general than considering this class of models. Problem now is to find a prior for the random probability that leads to a closed form expression for example, the posterior or the predictive. Now this stayed an open problem for 50 years, more or less, until Ferguson in the 70s came up with the definition of the Dirichlet process. And I believe that in 1 month or so, there will also be a conference to celebrate the 50 years of the Dirichlet process. So what is the main idea of the Dirichlet process? Well, it is an almost surely discrete random probability. So this means that you will have an infinite sequence of atoms and an infinite sequence of jumps. There are many ways of introducing the Dirichlet process. I will use the one that is, let's say, more important for the rest of the discussion, which is to introduce it as a normalized gamma random measure. So what is the idea? You know that very often, even with standard probability measures, you often define them as a normalized measure, basically because it's easier to treat the measure than the normalized measure. Well, actually, it turns out that you can do the same thing with random probabilities. So it's usually easier to treat the random measure rather than the normalized random measure. And so one way to define the Dirichlet process is through a normalized gamma random measure. Now, we will say more about these gamma random measure. For the moment, I'll just tell you what happens to the inference and predictions and why the Dirichlet process is really the cornerstone of the entire field. So basically, if you use a Dirichlet process as a prior for your random probability in this model, it turns out that there is a closed form expression, both for the posterior and for the predictive. So let's comment a bit on the prediction. So here you can see that your prediction will be a convex combination of two terms. One is P0, which is a parameter of the distribution, and one is the empirical measure, so the observation that you see in your data set. So P0 here can be interpreted as your prior distribution for the observations. And so in this sense, you see that the predictive has something that will remind you of the normal, the posterior with a normal model, right? Because the predictive is a convex combination of your prior and the empirical data. Then, given this interpretation, the parameter alpha over alpha plus naught can be interpreted as how much weight you give to the prior. And alpha is another parameter of your law. And so you can govern both your prior guess and how much weight you want to give to your prior guess. Okay, so this makes, let's say, the Dirichlet process the cornerstone of Bayesian nonparametrics, and also ends what I wanted to tell you about Bayesian nonparametrics in general. Now we can move to on why we are interested in understanding the merging of opinion in a Bayesian nonparametric context, and why we can frame it in terms of a distance between random measures. So we have said that the Dirichlet process leads to this very interpretable form for the predictive distribution. But now, if you think about it, the coefficient alpha over alpha plus n can also be interpreted as the probability of seeing a new observations, right? Because if you do not sample by P0 and you sample from the empirical, you will be sampling from some observation that you have already seen. And so this means that the probability of seeing a new observation only depends on the number of observations that you have seen in the past, and not on which observation you have seen. So if I've seen 1, 1, 1, 1, or 1, 2, 3, 4, 5, nothing will change. The probability of seeing a different observation, a new observation, will stay the same. And so for this reason, there have been many proposals in the Bayesian nonparametric literature on how to make these predictive schemes more flexible. And one general class of such proposals is the so-called normalized, completely random measures. So I will be saying a bit more about this class. what I want to say right now is that they indeed entail more flexible learning schemes, so with a probability of new observations that also depend on which observations you have seen. But at the same time, they also have, let's say, more mathematics involved with both their definition and their computational tractability. And so somehow one could ask, when is this price in terms of mathematics and computations worth paying? In the sense, when does using a different prior actually lead to a different outcome? Because if I use a different prior and I obtain the same outcome, then probably I'm happy with the Dirichlet process and there's no need to go further. So this was somehow the motivating question. Of course, to answer it, we first have to say a bit more about what are our parameters and what is our merging of opinion. So we said that we can see the Dirichlet process as a normalized gamma random measures. Now what happens is that if you want to define different priors, what you can do is basically choose another random measure, so other than the gamma, or maybe choose another transformation, so other than normalization. And this provides somehow a general strategy. And when you choose completely random measures, which basically are a generalization of the gamma, which translates the idea of independent increments in the sense of the random measure. So you will have evaluations of the random measures on disjoint sets that are independent. Then, under some conditions, you can prove that, for example, normalization is defined in general. Then we will focus the presentation on normalization, but let's say that there are also other transformations that one can use. And this usually depends on what is your finite object of inference. So if you're interested in densities or kernel rates, a popular transformation would be kernel mixtures. If you're interested in survival functions, maybe exponential transformation. Anyway, just to say that there is more than one option. And finally, the class of models we will be focusing on are of this form. So we will have observations that conditionally on a random measure are IID from a transformation of the random measure, and then as a prior for the random measure, we will use one of these completely random measure. Our goal then is translated in the following. Find a distance between completely random measure to assess the merging of opinions, and find techniques to make it treatable both a priori and a posteriori. Okay, so now this will be the most technical part, but bear with me 1 second. So a bit about these completely random measures. They're really nice objects in a sense. So they have this very intuitive definition. I'm only asking that if you evaluate the random measure on this joint set, then you have independent random variable. And yet, with only this definition, very simple and very general, you can immediately prove that this entails that the random measure is almost surely discrete. So once again, you will have an infinite sequence of jumps and an infinite sequence of atoms. Now, this is a random measure, not a random probability measure, so the jumps do not have to sum up to 1 almost surely. Now, if I give you this definition, let's say it's very intuitive to grasp. At the same time, if I ask you, provide me with a law for a completely random measure, it's difficult from this general definition to come up with one. In this sense, there is the Lévy-Khinchine representation that comes up to help, and basically tells us that you can characterize the Laplace transform of the random measure, which characterizes its law, in terms of this measure nu that you see in orange over here. So nu is called the Lévy intensity of the completely random measure, and it lives on the joint space of the atoms, that is our observation space X, and the jumps, which are between 0 and plus infinity. So we can disintegrate the Levy measure in two parts. There will be a jump component and an atom component. So in general, they can be dependent, but in this talk, for simplicity, we will just assume that the jump component and the atom component are in product form, okay? So we will have this integration over here. Now, the atom component is a very simple object. So P naught, the atom component, is simply a probability distribution on X, the space of observations. And one can prove that the atoms of the completely random measures are actually IID from this P naught. The jump component is a stranger, more strange, yes, object, in the sense that not only it is not a probability, but rather a measure, it also has infinite mass around the origin. So it is a measure with infinite mass. Of course, it's not exactly equal to the distribution of the jumps because it's not a probability, but one can show that it determines the distribution of the jumps, and in that sense, it makes sense to call it the jump component. Okay, so just to give you an example, in the case of the gamma random measure, this is the corresponding Levy measure. Here you have this jump component, which you can see diverges near 0, and then you have P naught, which is a standard probability measure. And so even if this seems, not really straightforward, but if you think the Levy measure reduces a lot the complexity of the law of a random measure. So we have reduced something that is an infinite dimensional quantity as a random measure, a completely random measure, into something which is a measure on R. Of course, it has infinite mass, but it's still a much more tractable object. And so, in practice, what you know about completely random measure is their Levy measure. And so our idea to define a distance between completely random measure has been to define it exactly in terms of the Levy measures. Okay. So, we will have two completely random measures. Each random measure is characterized by a Levy intensity, which is of product form, a jump component and an atom component. Our idea is simply to define a distance between a completely random measure as a distance between the atom component plus a distance between the jump component. I call them J and A, jump and atoms. It will be useful afterwards. So for the atom components, we have two probability measures, standard probability measures. For example, two normal distributions on R. So we can consider one of the many distances that we have at our disposal, and we focused on the Wasserstein one. So for who does not know the Wasserstein distance, it has this very convenient representation when you look at the distance for random variables in R. So it's simply the L1 distance between the CDFs. But then we also have to compare the distance between the jumps. And now the jump component are measures with infinite mass. So it does not seem straightforward to understand what kind of distance we could use in this situation. But fortunately, there is an extension of the Wasserstein distance, which was defined in this paper in a more abstract context. And one of the features of this extended Wasserstein is that it enables to compare measures with different masses and eventually even infinite ones. So our scenario. And what we proved is that when you restrict to Levy measures on R, so between 0 and plus infinity actually, then we recover also for this distance between infinite dimensional quantities a very easy expression. So here you see this is the L1 distance between the tails of the Levy measures, which makes sense because the CDF wouldn't be defined if you have infinite mass around the origin, but the tail can be defined. And so this is the expression of the extended Wasserstein distance. Okay, we have all the components. Then, in order to also motivate some intuition of why we should choose this distance, we prove the following result, which basically tells us that if you consider the random measure and you consider intervals of the random measures, which will be random variables on R, then if you consider the standard Wasserstein distance between the intervals, this will actually be dominated by our distance. Okay, so there are two other challenges, if we want, that are really important for the work, but at the same time I won't be dwelling in this presentation. I'll just mention them. So first of all, a problem of identifiability. So are we sure that two different completely random measures, if you normalize them, you cannot find the same random probability? And actually, no, it's true. So there is more than one complete random measure that leads to the same normalization, but we characterize the entire set of completely random measures that leads to the same normalization. And so we focus on one representative of each class. Then the second problem is the one of conjugacy, because so we have defined our distance between completely random measure. But it turns out that even if you use a completely random measure as prior, then your posterior will not be a completely random measure anymore. It will be a completely random measure only conditionally on a random variable. Okay? So we have what we call the Cox completely random measure, in analogy with the Cox-Poisson processes, if someone knows about them. Okay? We will have a random Lévy measure, and so we have to treat a distance between random Lévy measures as well. Okay, so this is all the technical development for the distance. We now have a distance between completely random measures. I showed you the one a priori. I hope you will trust me on the fact that you can use it also a posteriori. And now we can go to seeing what are the findings that we can have for Bayesian non-parametric models a posteriori. So the first question that one may ask is, if now I consider two Dirichlet processes where I change maybe the alpha parameter or the prior guess on the distribution P0. What will happen to my posteriors as I see more and more data? Will they eventually merge? So to study this problem, we know that the Dirichlet process is a normalized gamma random measure. So we consider two gamma random measures with different alpha or and different values for P0, and we study the distance a posteriori between the random measures. So this distance a posteriori will have two components, J and A, which reflect the difference between the jumps and the difference between the atoms, which comes from how we define the distance itself. And so these are the expressions. So I don't want for you to look at them too much. What I want to underline about these expressions is that they're really in closed form and easy to sample, or to approximate numerically. So basically, we have reduced a distance between infinite dimensional quantities in a form which is really an analog of what you would have between, for a distance between finite dimensional quantities. So now, if I want to study this problem, what I can do is try to define different values of alpha, different values of P0, and simply plot the distance and see what happens. Of course, this is what we did at the beginning, but then we thought, can we say something about even data sets that we have not seen? So can we generalize and find some properties that hold in general for our merging? And so to do so, what we need to do is to basically study the asymptotics of these expressions over here. And since we have them in an analytical form, we are actually able to do that. So these are the findings. First of all, if you consider two-leadership process, there will always be merging of opinion under these mild assumptions. So basically an integrability condition on the data, which again does not mention what is the true distribution of the data, okay? Then, we can also find the merging rate, which will always be 1 over n. So it's not affected by what choice you did about alpha or p naught. And importantly, it's not even affected by the dimension of the space of your observations. And finally, we can also ask when does the merging start. And here we see that there is a different behavior for the jump and the atom component. So for the jump component, we can prove analytically that it's always decreasing. So this means that for the jump component, the merging will start immediately. With the first observation, your distance between the jumps will be smaller. For the atom components, we can have a different behavior. So when the two alpha parameters, so how much you wanted to trust your prior guess, are equal, then you can prove analytically that also the distance between the atoms, so the atom component, is also decreasing immediately. So the merging will start immediately. When the two base probabilities, so when your prior guesses P naught are equal, the situation is different. So basically your merging will not start immediately, but rather after a while. Then you know that it will happen, right? Because we proved that it's equal to 1 over n overall. And we can also somehow characterize when the maximum will be reached. So what is the maximum value of the distance before it actually decreases? So this is, I think it has a quite fun interpretation for Bayesian inference, because basically it's telling you that even if two Bayesian have the same prior distribution on the data, so the same P naught, and they see the same observation, so the same data, the distance between their posteriors can actually increase depending on how much they're willing to trust their prior guess. So how much they will move towards the observations. Okay, and then we also focused on a different normalized completely random measure, which is often used in Bayesian non-parametric inference, and it is generalized gamma CRM. So as you can imagine from the name, it generalizes the gamma. And in particular, there is this parameter sigma that when it goes to 0, the generalized gamma actually converges to a gamma. So this generalized gamma prior is known somehow to be strongly affected by the choice of the parameter sigma. And so what we asked is, let's try to understand if we can characterize and study the merging of opinion in this setting. So between a gamma and a generalized gamma. So once again, we considered the random measure and studied the distance between the posteriors. And so here, you see in the theorem here, we have a completely different situation than what we saw for two gammas. So if you remember, the merging rate for two gammas was always 1 over n. Now you see that there is a phase transition. And this depends on k, which is the number of unique observations in your data set. So basically, from this expression, which sounds a bit analytical, but what are the main messages that we can extract? So first of all, that whereas with the Dirichlet process there was always merging, here we have that we have merging of opinion if and only if the number of unique observations is strictly slower than the number of total observations, n. Then we also see that whereas with the Dirichlet process the merging rate was not affected by the choice of parameters, here yes, right? Because we see that if we are in the regime on the left, then the merging rate will depend on sigma, which is a parameter of one of the two prior that we are considering. And so finally, to answer the initial question, when does a different prior actually lead to a different learning outcome? Well, now we can answer to this question explicitly for the generalized gamma. So it will have a different outcome whenever either the number of observation is small, which probably is what one would expect, or the number of unique values, k, is large. And basically how large and how small it must be, we can explicitly characterize it in terms of the parameter sigma that we're using for our generalized gamma prior. Okay, so this is what I wanted to tell you. Now it's just simulations and reassuring plots, basically. So what we did was to basically consider simulated observations where we knew that we were in one of the two regimes, okay? So in one case, k, the number of unique observation being smaller than that quantity over there, or the opposite. And this can be achieved by considering distributions, observations that are conditionally IID, given a specific prior. In one case, the Dirichlet process on the left, and in the other, the Pitt-Magnol process. I won't say anything about it, but just to say this is the simulated data that we considered. And we knew from the theory that the rate was exactly in one of the two regimes. And so we plotted the distance between the posteriors to look if our rates were actually correct. And so here you see this different situation. So if you remember, in the expression here, we would have, for the first regime on the left, we expect to see a dependence on sigma, on the choice of parameter sigma. For the second regime, no, because it only depends on the number of unique observation in the data. And so here you can retrieve this interpretation. So on the left, you see that the distance, the distance between the posteriors actually decays with a different rate depending on the choice of parameter sigma. Whereas on the right, you see that the rate stays the same because it only depends on the number of unique observations in the data set, which are the same for each situation. Okay, so recap. So what have we seen in this talk? So first of all, we have defined a notion of optimal transport between completely random measure. So this is probably the first contribution. Then we used this distance between completely random measures to define a notion of merging of opinions in a Bayesian non-parametric context. And we have used it to understand what is the impact of the prior in our posterior inference. And finally, doing this case-by-case scenario, we observed that there are many different settings that can occur. So the merging can occur, but it can also not occur, as we have seen with the generalized gamma theorem. It may vary, the rate may vary according to the prior, because we saw that in some cases it depended on sigma, and in some cases it didn't. And moreover, the merging can start immediately or after a while, as we have seen with the case of the two Dirichlet processes. So it's, yes, it's a strange question, I think, for I mean, interesting question for a Bayesian non-parametric context. Future work. So if you think about it, we have focused the entire talk on normalization of a completely random measure. But at the beginning, I had mentioned that you could consider other transformation as well. So for sure, one first thing to do would be to extend this framework to other choices of transformation. Then another direction I think is interesting is the following. So if you think we have used two different priors and same data, but we could also analyze the situation of same prior and two different data sets. And so if you use a distance between the posteriors in this setting, then you could actually use it to perform homogeneity sample tests between two different groups, or maybe even robustness questions of the type, if I perturb the data a bit, will the two posteriors be close to each other? And finally, as a general thought, I think that there is still a lot of work to be done in terms of what is a good distance between random measures. But once we actually arrive to finding a distance that has all nice properties that we would want from a distance, so tractability, being able to sample from it, and so on, then I think it could be a really nice thing to have in a Bayesian non-parametric context, because there are so many methods that use distances in a Bayesian parametric setting that could actually be extended to a non-parametric one as well. Okay, so thanks a lot. This is joint work with Ugo Lavenon from Bocconi University, and we have an archive paper here if you're interested. Thanks.
Okay, is there any question?
I was wondering, is there a connection between this notion of merging of opinion and the notion of prior robustness? If you have a good, and if the answer is yes, how do you translate your findings into a recommendation for user, how to choose the priors? So I guess what you want is recommend priors or ways of choosing your priors so that you're more likely to, that your opinion merge, right?
Yes, no, that's a great question. So somehow you can use a distance also for robustness with respect to the prior, as was suggested, in the sense that you could think of a small perturbation of the prior and check whether the posterior is also close to what you would get. So in that sense, I think that you should be able to readapt our calculation. So it wasn't our immediate goal because we were also interested in seeing when the priors are far apart. Not, but yes, I think it should be able to replace it. I think, yes. So probably in that sense, for the Dirichlet process, of course, you would have a strong robustness to the choice of parameters, whereas with the generalized gamma, you probably have to be more careful. Again, it also depends on the data that you have, and I expect it to depend explicitly on the number of unique values that you have. Okay. But thanks, yes, it's a great question.
But you have to look at the data then.
Not look at, yeah, that was a bit of the sense. You do not have to, you can summarize the characteristics of the data if you want, right? You only have to look at the so my guess, okay, I haven't done it. My guess would be that you can characterize it in terms of how many unique values you have in the data, okay, which is easy to look at, I guess, from a plot or something. But yes, thanks.
On the practical ground, there is a lot of work on expert elicitation for prior. Mm-hmm. I'm thinking of the team of Professor O'Hagan in Sheffield.
Yes.
Do you know anything about expert opinion with a non-parametric Bayesian model?
Well, I think you can encode it very naturally in a Bayesian non-parametric context. at least for example with the Dirichlet process, where your alpha and your P naught are so easily to interpret, then I guess that P naught would really be your prior guess that could come from experts or from a prior experiment, maybe different data set, but a similar one. And your alpha can be how much you trust it, for example, how many studies confirm it, or so on. Then I'm not sure if this is exactly the answer to what you're asking.
No, I was just curious about it. Because I can see how I would do in practice in a parametric framework.
Okay.
But I think it's rather tricky in a non-parametric
yes,
framework.
so I don't know which techniques you're referring to exactly, but maybe if I can see the analog to in the parametric case, maybe I can come up with a more precise answer.
Thank
Thanks.
you.
Hi, thanks a lot. I was wondering whether you could use the merging of opinion for an idea of model choice, where say I want to compare two models and one has more parameters, then one way of framing that is saying that the prior for the simple model is to be theta 1 has to be equal to 0.
Mm-hmm.
So is there a possible link, and could you use that, I don't know, instead of base factors, for example?
That's interesting. Yes, so it would be a one sample, if you want, test. So of whether the value of a parameter should be equal to 0. But yes, it makes sense.
One thing you could say is, like, if the simple model is the correct one, then they should merge.
Yes.
And if it's not the correct one, then they shouldn't merge.
Yes, yes. Yes, it makes sense. It makes sense. Yes, I hadn't thought about it, but absolutely. I would say it would be. Thanks for the suggestion.
Other question? No? It's okay. So thank you very much, Marta, again.
Thank you. Thank you.
And